Okay, I want to finish up this set of content by having us think about something which you might have encountered or you might have given some thought to before, but I just want to formalize some of that thinking. And that's the importance of self-assembly. So what we mean here is how do we get more complex cellular structures using only 4 types of macromolecules? So how do we get mitochondria, or how do we get the endoplasmic reticulum? When we're only considering really 4 types of macromolecules, how do we go from that relative simplicity to considerable complexity where we see most of the important functions in the cell? So let's start off with a basic principle. This principle of self-assembly really says that the information that you need to specify the folding of macromolecules such as polypeptides, as shown here, and then their subsequent interactions to form complex structures, are inherent in the polymers themselves. So the polypeptide on the left, and that's what comes out of the ribosome, will fold in some cases spontaneously into this protein on the right, and proteins are folded polypeptides. Polypeptides are chains of amino acids. Now, the information to give you the complex 3-dimensional structure of the mature protein is inherent in the sequence of amino acids. It's that sequence of amino acids which gives you particular secondary structures, and then gives you particular tertiary, and then in some cases quaternary structures lead to a fully functional folded 3-dimensional protein structure. So that's a very, very simple case of self-assembly. In some cases, you do need assistance, or these molecules do need assistance from something called molecular chaperones. Because what they do is they prevent incorrect structures from forming, and thereby promote the formation of the correct structures. And so if we're looking at hydrophobic interactions, then amino acids with hydrophobic R groups are going to self-assemble into clusters of hydrophobic cores, for example, to give us a hydrophobic core in a polypeptide. And we often call that correct folding, the correct conformation, or the native or natural conformation. And you can change that by obviously changing the ionization state of certain R groups, by changing the pH. You could change temperature, for example, to interfere with hydrogen bond formation. And so you can change the native conformation into a non-native conformation by affecting cellular conditions through changes in pH, loss of buffering, changes in temperature, that kind of thing. Now, fortunately, those things are under homeostatic control, but if they're not, and we lose buffering capacity, for example, then we see a loss of native conformation in polypeptides, for example. Now you can reverse the folding in a process called denaturation, and so excess heat, extreme changes in pH, which change ionization of the R groups, can lead to denaturation, and that's where they go back to being unfolded. Now, if you change the conditions back to suitable conditions, then in some cases the molecule will renature and form. This applies to RNA molecules as well, where there is extensive secondary structure. If you heat them up and you unfold them, you can then remove the pressure that left them unfolded, the pressure being heat, for example, that kind of thing, not actual physical pressure, and they will refold due to the inherent sequence of the monomers in the polymer. And when you don't get that happening, normally, sometimes you do need molecular chaperones. And now the same kind of principle applies for us when we consider forming more complex structures. So it's the inherent structure of proteins and lipids which give the self-assembly to structures like mitochondria. So when we look at the cristae, for example, the folding that you see in the cristae is due to the arrangement of certain proteins in the U or the bend of the cristae, and those proteins will go there to some extent on their own and cause this particular structure, which is then obviously an important function of the mitochondria to increase surface area via those folded cristae. There are other structures that you know about which are capable of self-assembly. Ribosomes, for example, they self-assemble. The components being produced in a nucleolus, for example, exported to the cytoplasm, and then we see self-assembly on messenger RNA to initiate translation. So again, the the consequence, if you like, the consequence being the formation of a complex structure, is completely inherent in the properties of the pieces. And this leads us kind of back to an idea from general biology of emergent properties. We see new properties and new characteristics arising because of the ability of individual pieces to self-assemble. So ribosomes are a good example. Membranes are a very good example. So I think your textbook also has a very long discussion about the self-assembly process in viruses, and that may help to kind of cement this idea a little bit. I'm going to finish up here just by looking at the whole hierarchy, if you like, all the way from the individual monomers all the way up to the complex structure of the cell, which at that point we say then we have life, and life then is the emergent property from the in many cases self-assembly of macromolecules into more complex supramolecular assemblies such as membranes and mitochondria and that kind of a thing. A lot of this assembly is hierarchical in nature, and that means there are levels to the organization. And so if you think about the cell as a whole, the cell is formed from collections of organelles, including cytoplasm, if you want to consider that an organelle. I don't, but if you want to think about everything that makes up the cell as an organelle, then you could consider it as assemblage of the organelles plus the cytoplasm, and those are made from things like membranes, proteins, carbohydrates, lipids, and we go back down another level and we're talking about the monomers which are used to synthesize those macromolecules. And so to get to the level of complexity of a complete cell, we have this hierarchical assembly. Now, you can ask yourself why have this hierarchical assembly, and there are three main benefits to it. First of all, it lends itself to chemical simplicity. You only need a relatively few subunits. You only need the subunits to make polysaccharides, proteins, lipids, and nucleic acids. If you've got those basic subunits, then all you need to do is the condensation chemistry to build up those organic monomers into more complex polymers, and then you have an efficiency of assembly. You don't need much chemistry to get these things constructed. You can also have good quality control as well. You can stop a complex structure that's defective appearing by removing a defective subunit of that. So if you've got a defective tubulin molecule, you can remove that. You don't have to wait till you get to the point of having a defective microtubule to then decide that you need to recycle the whole microtubule and break it all the way down. You can eliminate the misfolded tubulin protein, for example. So you've got chemical simplicity and efficiency of assembly and quality control so that you can discard defective components before you have built the complete thing, and that's a waste of energy and materials. So cells have a certain inherent ability to self-assemble. There are cases when the molecules need assistance, and in that case we use molecular chaperones which aid the folding, and that principally applies to polypeptides folding in to proteins. So that's what I'm going to say on the topic of self-assembly. That's a little bit new, so make sure you focus on that and read a little more extensively around it. That brings us to the end of chapter 2. Next thing we're going to look at in a little bit more detail are some of the macromolecules. We're not going to cover all of the macromolecules because that's usually done extensively in general biology. We're just going to review some of the important points about macromolecules and hopefully introduce a little bit of new material. So I'll see you next time when we start chapter 3.